Hey guys, it's Jalal Jora here again, back with another video from BAGM at GCSE Chem. How are you guys? I didn't ask that before, but yeah, how are you guys doing? It's Jalal Jora here again from BAGM at GCSE Chem, and today we're going to be doing C2.5. So just repeated the intro there. Yeah, I'm really sorry, but I'm actually recording this very late. It's 11:13 p.m., so very late today. I think it's my latest recording so far in like all my videos, and you know. And today we're doing C2.5, which is explaining the trends that we basically learned about in C2.3 and C2.4 of Group 1, the alkali metals, and Group 7, the halogens, respectively. So this is the book I'm using, the AQA GCSE Chemistry Caboodle Revision Guide. And yeah, so as I said, today we're doing C2.5, which is explaining trends. And also, I couldn't, by the way, put the C2.4 on my website, so I'll try and do that today. And I'll also put the C2.5 one that we do on explaining trends. I'll also put that link to that video also on my website. So yeah, so I'll obviously I'll try and do that. So, sorry about that. Sorry about what happened there, but yep. So basically, let's get on with the video. Let's get on with the lesson, basically. Reactivity within groups. So reactivity within groups. So let me start again. C2.5, explaining trends. And yeah, if you're following the student book, it's pages 30 to 31. And reactivity within groups. So within a group, the reactivity of elements depends on the total number of electrons. Going down a group, there are more occupied energy levels as the atom, or energy levels, yeah. So going down a group, there are more occupied energy levels, and the atoms get larger. As the atoms get larger, the electrons in the highest occupied energy level or outer shell are less strongly attracted to the nucleus. So obviously this is something I'm going to have to really explain. But basically, as you have the nucleus with shells and everything. So basically, the further you are from the nucleus, obviously the weaker the attraction between the nucleus and the outer electron. Sorry about that again. But so as atoms get larger, the electrons in the highest energy level are less strongly attracted to the nucleus, because obviously the nucleus is in the center, remember, and the outer electrons, the further you are, the further those outer electrons will be from the positively charged nucleus, and so therefore they're more weakly attracted, and so less strongly attracted. So that's basically, why, this is basically, what happens going down a group. They're more occupied energy levels, and the atoms get larger, and therefore the electrons in the highest energy level or highest out or in the outer shell are less strongly attracted to the nucleus, because obviously there are more shells within it. The more inner shells, basically, as the atoms get larger. So hopefully that makes sense. And also 1 minute. Sorry about that. But the inner shells of electrons screen or shield the outer electrons from the positive charge of the nucleus. So that's very important. I think it's better to say shield the outer electrons from the positive charge of the nucleus, rather than saying screen the electrons. Shield is a better word. I think shield is the word that's going to get you marks, not screen. So when metals react, they lose electrons, so the reactivity of metals in a group increases going down the group. So as you go down the group, the reactivity of metals increases down the group, and that's obviously why that obviously makes sense, because group 1, which are the alkali metals, group 1 elements, which are alkali metals, their reactivity actually increases down the group, and then when non-metals react, they gain electrons. So the reactivity of non-metals decreases down the group. Again, like non-metals like group 7, which are the halogens, the reactivity, as we know, decreases as you go down the group, and obviously they gain electrons. So, it makes sense. Now, why do metals get more reactive going down the group? So obviously metals, well, the answer here, so here's a question. So the answer is obviously, well, it's because metals lose electrons, and basically as you go down the group, so as you go down the group, there are obviously more occupied energy levels, the atoms get larger, and then therefore this means that the outer electrons basically are much, much weakly attracted to the positive charge of the nucleus, or much, they're much less strongly attracted to the positive charge of the nucleus, if that makes sense. So therefore, they're more. The outer electrons are, the inner electrons actually shield the outer electrons more as the atom gets larger. Basically, as the atoms get larger, the outer electrons are further from the nucleus. They're less strongly attracted to the positively charged nucleus, and that's basically the answer. You have to say that. So atoms get larger, and the number of occupied. The number of occupied energy levels increase, the number of shells there are increase, and basically this means that the outer electrons are less strongly attracted to the positive charge of the nucleus, or to the positively charged nucleus. So that's the answer for if they ask you that. But let me just confirm with the book, just to make sure I'm on the right track, I'm saying everything right. So yeah, when metals react, their atoms lose electrons. Atoms get larger, there are more occupied energy levels, and the electrons in the highest occupied energy level or outer shell are less strongly attracted to the nucleus, and so will be lost more easily. Yeah, one thing I forgot to mention is because they're less strongly attracted, they're going to be lost more easily, because obviously if something is less strongly attracted to something else, it's more likely that there will be that it will go away. No, like it's more likely as you go down the group for group 1, for example, it's more likely that francium will lose its electron than lithium, because obviously francium is a much bigger atom, greater distance between the outer electron and the positive charged nucleus. So therefore, the outer electron is much less weakly. Less strongly attracted to the positive charged nucleus. So the outer electrons are less strongly attracted to the positively charged nucleus. Hopefully that makes sense. Hopefully you can get all that wording in what I just mentioned. Now we're going into explaining the trend in group 1. So we know reactivity increases going down group 1, and because the outer electron is less strongly attracted to the nucleus, as the number of occupied energy levels increase. As the number of occupied energy levels increases and the atoms get larger. Again, similar to what we said before, as you go down the group for group 1, the reactivity increases. We basically answered that when they asked why do metals get more reactive down the group, going down the group. Well, we just said that the outer electrons they're less strongly attracted to the positively charged nucleus because there are more occupied energy levels or shells. So occupied just means filled with electrons. Sorry if I'm having to repeat myself and stutter a couple of times. It's after 11. My brain sometimes gets weird. Let me just say that that's the reason why I'm stumbling a bit, but hopefully it's okay. So yeah, the outer electrons are less strongly, or outer electron, because there are only one outer electron in group 1, is less strongly attracted to the positive charged nucleus. There are more occupied energy levels or shells, and also the atoms are larger. Atoms get larger as you go down the group, so the electrons are more easily lost. I actually forgot to say this point when we were answering the question, why do metals get more reactive going down group 1? But you must also mention that because the atoms get larger and because there are more occupied energy levels and because it's the outer electron or outer electrons, if you're talking about other metals apart from group 1, apart from other elements apart from those in group 1, then you have to say outer electrons are less strongly attracted to the positively charged nucleus. So yeah. So and then after all that, you have to say therefore, the electrons are more easily lost, and therefore it's more reactive. The reactivity increases as you go down the group for metals, basically. And that's the trend for group 1. And explaining the trend for group 1, that's the one there. And then the attraction of the nucleus for the outer electrons is also reduced by the shielding effect of the inner shells. So the attraction of the nucleus, let me read that again. The attraction of the nucleus for the outer electrons is also reduced by the shielding effect of the inner shells. Yeah. Basically, if you have greater shielding by inner shells, it means that the attraction for the between the nucleus and the outer electron, basically, or the outer electrons, if you have more than one in the outer shell, is basically reduced, and that's due to the effect of that's due to the shielding effect of inner shells. So that's fine. And then so here's a diagram showing here's a lithium atom. Here's a lithium atom. Here's a sodium atom. Is that sodium? Yeah, there's sodium. As you can see, sodium atom has one more shell than lithium atom, so greater shielding. So the distance between the outer electron and the positive charged nucleus is greater for sodium than lithium. There are more occupied shells. There is an extra occupied basically shell in sodium than in lithium, and therefore it's more easy to lose that electron because the atom is larger as well for sodium than for lithium. So hopefully that makes sense. So that's what you have to explain for a 3-4 mark question, maybe even a 5 mark question on why maybe sodium is more reactive than lithium, or anything else basically. And they could ask you about other elements too. So here it says this electron is easier to remove than the outer shell, than the outer electron in a lithium atom. So outer electron in a sodium atom is easier to remove than that of a lithium atom, purely because of the fact it has one extra shell, and what I just talked about before, larger atom and all that. So why is so obviously here sodium's outer electrons are further from the nucleus. So sodium's outer electron, because there's only one of them, is further from the nuclear charge, and that just means positive charged nucleus, and is shielded by more inner shells of electrons than lithium's outer electron, because there's only one electron in outer shell for group 1 elements, the alkali metals. Now, why is lithium less reactive than sodium? Again, we've gone through that. Lithium is a much smaller atom. It has, the outer electron is much more strongly attracted to the positive charged nucleus than it is for sodium, and basically, they're more. There are actually less occupied energy levels or shells for lithium than it is for sodium, basically. So hopefully that should be the answer, and then explaining the trend in group 7, and then we're nearly done. So we just go through this. Sorry if my face is hidden sometimes, but what is it? Lithium's outer electron is close to the nucleus and therefore is more firmly held. Yeah, I said the outer electron is more strongly attracted to the nucleus. Therefore, you can also add this. It's more firmly held and more strongly attracted. It's less likely to just go out, and lithium's less likely to lose its electron than sodium. Explaining the trend in group 7 now. The reactivity of halogens decreases down group 7, so we went through that yesterday in C2.4, and that's because the attraction of the outer electrons to the nucleus decreases as the number of occupied energy levels or shells increases. So obviously, as the number of occupied energy levels or shells increases, the attraction of the outer electrons decreases. Now, more inner shells also shield the outer shell. So more inner shells also shield the outer shell, reducing the attraction for the nucleus for an incoming electron. So basically, as the atom gets larger in group 7, basically there's less attraction between the outer electrons and the positively charged nucleus, and therefore it's harder for the positive charged nucleus to actually for the atom to gain an electron and form an ion. As you go down the group, this reactivity have to obviously decrease. As the number of occupied energy levels or shells increases, the attraction between the outer electrons and the positive charged nucleus decreases. And basically, a larger atom, you could say, as you go down the group again, and therefore, less likely, it's harder to gain an incoming electron. And basically, it's very similar to what we said before, but just in the opposite context. Like, you should be able to know, like what I just said there. You should be able to understand that, hopefully. Don't need to go through that much, through that in detail. But this is actually very, very important. Explaining trends is very, very important in chemistry, and it's actually built upon in A-level chemistry as well. yeah, I'm not going to tell you about what we do in A-level chemistry because, that's a secret. Only A-level chemistry students should know what you do in A-level chemistry because they're the ones picking the subject, so they're the ones that should be interested in it. I'm not trying to, sound harsh. Just pick A-level chemistry, then you'll know all the interesting stuff. Now, study tips. So in group 1, elements lose electrons when reacting, so reactivity increases going down the group. Now, however, in group 7 elements gain electrons when reacting, so reactivity decreases as you go down the group. So basically, it's the opposite for group 1 and group 7, and hopefully you understand this. If you don't understand this properly, I recommend you going through the student book, checking, that's got it in more detail. This is obviously just for a brief refresher, once you've actually done the topic. So yeah, and it's, as I said before, it's pages 30 to 31 in the student book, the big book, basically, the big textbook. Now, the key points just to finish off, so there are quite a few key points here. So you can explain the trends in reactivity as you go down the group in terms of attraction between electrons in the outermost shell and the nucleus. So you can explain that, obviously. Yep. So attraction between electrons in the outermost shell and the nucleus. So yeah, that's the main thing. The attraction is basically the main basis of all this. The distance between the outermost electrons and the nucleus. So sorry, the electrostatic attraction. Now we're going on to the second one. The electrostatic attraction depends on. So that's obviously between the outer electrons and the positive charged nucleus. So that depends on the distance between the outermost electrons and the nucleus, the number of occupied inner shells or energy levels of electrons, which provide a shielding effects, and the number of inner shells that you have, which obviously provide shielding for outer shell of electrons, inner shells of electrons providing shielding for outer shells of electrons, and finally the size of the positive charge on the nucleus, called the nuclear charge. The greater the nuclear charge, the greater the reactivity. In deciding how easy it is for atoms to lose or gain electrons, so this is the final point, in deciding how easy it is to lose or gain for atoms to lose or gain electrons from the outermost shell, these three factors must be taken into account. The increased nuclear charge due to extra protons in the nucleus going down the group is outweighed by the other two factors. Basically, what they're saying is nuclear charge basically takes priority over the other two factors, which are shielding and also I think it was distance between the nucleus as well. Yeah, distance between the nucleus and the outer electron. Or outer electrons. So therefore, electrons are easier for larger atoms to lose going down the group, and harder for them to gain going down the group. So obviously, group 1 elements, obviously, it's easier for them to lose electrons going down the group, and it's harder for group 7 elements to lose electrons. Let me say that again. So it's easier for group 1 elements to lose electrons going down the group, and it's harder for group 7 elements to gain electrons going down the group. So hopefully that makes sense. That's the end of section C 2.5, explaining trends. I really hope this video was useful. Make sure to share, like, and subscribe. Turn the notification bell on if you haven't already, so you're notified and updated basically when I upload new videos that you can watch. Sorry for my voice and sorry for any noise that was there. And I'll see you in the next video, which is only for triple science students only. I said only twice, but it's C2.6, the transition elements, and I'll basically try and get both of these videos, so C2.4 and C2.5, on my website today. Thank you very much, guys. See you tomorrow. Bye.